September 19th, 1944, 9:15 in the morning, Réchicourt-la-Petite, France. Lieutenant Edwin Leiper crouched behind a stone wall, watching fog roll across the open ground north of the village. Behind him, 3 M18 Hellcat tank destroyers from C Company, 704th Tank Destroyer Battalion idled quietly, their 76mm guns pointed toward the murk. The crews knew German armour was out there somewhere. Radio reports had warned that Panthers from the 113th Panzer Brigade were pushing toward their positions, attempting to cut off Patton's Third Army advance into Lorraine. What none of the German tank commanders knew was that they were driving into an ambush, orchestrated not by superior firepower or thicker armour, but by something they couldn't anticipate. Speed. The Americans had finally fielded a vehicle that could do what German doctrine considered impossible: outmaneuver Panthers at highway velocities, strike from angles the Germans never expected, and vanish before their hydraulically traversed turrets could respond. The psychological shock would be immediate and devastating. The fog lifted suddenly at 9:20. Leiper saw the muzzle of a Panther's 75mm KWK 42 gun emerge from the mist barely 75 yards away, its long barrel swinging as the crew searched for targets. Then a second Panther appeared, then 3 more. The German tankers were advancing in a column along the road, exactly as American intelligence had predicted. They expected to encounter dug-in Sherman tanks, perhaps some towed anti-tank guns. They had no reason to expect what came next. Leiper's platoon opened fire. In 5 minutes, 5 Panthers lay burning or disabled. German crews bailed from hatches, their confidence shattered. The remaining Panthers turned away, attempting to withdraw, but the Hellcats pursued them, racing across farm fields at speeds the German crews couldn't match. By the time the fog returned 10 minutes later, 10 more German tanks were destroyed. The Americans lost 2 Hellcats. Sergeant Henry Hartmann's M18 alone knocked out 6 Panthers, most at ranges under 1,000 yards, all struck in their vulnerable side armour before their crews could bring guns to bear. The engagement that morning would become one of the most lopsided tank battles on the Western Front, but more importantly, it revealed a truth that German armour doctrine had never accommodated. Sometimes the best armour is not being there when the enemy shoots. The crisis that produced the M18 Hellcat began 3 years earlier in the sand and rock of North Africa. Spring 1943, somewhere near Kasserine Pass. American M4 Sherman tank crews were getting slaughtered by German panzers in combat that exposed uncomfortable realities about American armour design. The kill ratios were devastating. For every German tank knocked out, the United States was losing 3 to 4 Shermans. A Panzer Mark IV could punch through a Sherman's frontal armour from 1,500 yards, while American 75mm guns needed to close to within 500 yards to scratch German armour. Panthers were even worse. Their 75mm KWK 42 guns could destroy Shermans at ranges exceeding 2,000 yards, while Sherman rounds often bounced off Panther frontal armour even at point-blank range. American tank crews developed dark humour to cope with the terror. They called their Shermans Ronsons after the cigarette lighter because they lit up so quickly when hit. Others called them Tommy Cookers. The jokes masked genuine fear. Army brass recognized the problem immediately. Reports from North Africa painted a grim picture. German tanks could kill American tanks at ranges where American guns couldn't penetrate German armour. These weren't tactics. This was a material disadvantage that no amount of training could overcome. The obvious solution seemed straightforward: build thicker armour, mount bigger guns, create American versions of the Tiger and Panther. But Brigadier General Andrew Bruce, head of the Tank Destroyer Command, approached the problem from a different angle. Bruce had studied German blitzkrieg tactics obsessively since 1940. He'd analysed every report from Poland, France and Russia, looking for patterns in how German armour operated. he noticed something crucial that most American planners overlooked. The side and rear armor on every German tank, including the dreaded Tigers and Panthers, was significantly weaker than frontal protection. A Tiger's frontal armor measured 100 mm thick. Its side armor measured only 80 mm. The rear was even thinner at 80 mm. Panthers showed the same vulnerability pattern. Their sloped frontal armor was nearly impenetrable to American guns, but their 40 mm side armor could be penetrated by 76 mm rounds at over 1,000 yards. Bruce's radical idea challenged everything American armor doctrine assumed. Don't try to outarm the Germans, outmaneuver them instead. The concept he championed became known as shoot and scoot. Get into position fast using superior speed. Take your shot at the enemy's vulnerable flanks, then disappear before they can return fire. It required completely rethinking armored vehicle design. Speed wasn't just a desirable feature anymore. It became the primary survival mechanism. In February 1943, Bruce's team at the Tank Destroyer Tactical and Firing Center in North Carolina started working with engineers from Buick Division of General Motors to create something that had never existed before. A tank destroyer that could outrun anything with tracks. The specifications they drew up seemed almost impossible to engineers accustomed to thinking about armor protection. First, they wanted a vehicle that could hit 55 miles per hour on roads, maintain 35 miles per hour cross-country, mount a gun powerful enough to kill any German tank from the side, and still remain light enough that existing bridges wouldn't collapse under its weight. For context, the M4 Sherman topped out at 25 miles per hour on good roads and felt like it was shaking itself apart at that speed. What Bruce was proposing was more than twice that fast. Engineers at Buick looked at those numbers and thought he'd lost his mind. But Bruce had done his calculations carefully. If his tank destroyers could move at highway speeds, they could respond to German breakthroughs 3 times faster than traditional armoured units, getting into ambush positions before panzers even knew they were in the area. The tactical advantage would be overwhelming, fast enough to dictate engagement terms, fast enough to strike and vanish, fast enough to make German gunnery irrelevant because you simply weren't there when their shells arrived. The biggest obstacle was power. Every tank engine in American service in 1943 was designed for compromise between power, weight, fuel efficiency, and reliability. The standard Wright R975 radial engine that powered the Sherman kicked out a respectable 400 horsepower, but it was already maxed out, pushing 33 tons of tank around. The Hellcat needed to be faster while carrying a crew, a 76mm gun, and enough ammunition to actually fight. The math didn't work with conventional thinking. Buick's engineers turned to an unlikely source: aircraft engines. The Continental R975 radial engine, originally designed for planes, generated 450 horsepower with a power-to-weight ratio that made automotive engineers take notice. The engine weighed roughly 1,500 pounds, but generated enough torque to move something 3 times the Hellcats' eventual weight. In April 1943, Buick received the contract to adapt this aviation power plant for tracked combat. The challenge was daunting. Airplane engines are designed to run at constant high revolutions per minute at altitude, not deal with the stop-and-go, low-speed grinding that tanks experience. Aircraft engines run smooth and steady. Tank engines need to lug through mud, climb steep hills from standstill, and idle for hours during ambushes. The operating conditions couldn't be more different. Buick's engineering team, led by Chief Engineer Charles Chain, had to completely redesign the cooling system. Radial engines are air-cooled and depend on propeller wash to keep temperatures manageable. In a tank, there's no propeller creating airflow. They solved this by installing 2 massive 11-blade cooling fans that could move 10,000 cubic feet of air per minute through the engine compartment, even when the vehicle sat stationary. The fans were engineering, marvels themselves, carefully balanced to prevent vibration and positioned to maximize airflow across every cylinder. The fuel system needed a complete overhaul too. Aircraft engines feed fuel through gravity or low-pressure pumps because they're always oriented correctly in flight. A tank climbs hills at 45-degree angles, crashes through ditches, tilts sideways on slopes. Fuel delivery can't rely on gravity when the vehicle might be upside down relative to level. Buick installed a pressurized fuel delivery system with multiple redundant pumps that could feed the engine regardless of the vehicle's orientation. Each pump had backup systems. If one failed, two others could compensate. The engine would keep running even if the tank was practically standing on its nose. Oil circulation presented another challenge. Radial engines normally rely on specific positioning for oil to flow properly between cylinders. The Buick team designed a dry sump oil system with external reservoirs and high-capacity pumps that ensured lubrication even when the Hellcat was climbing obstacles that would strand conventional tanks. The oil circulated constantly under pressure, coating every bearing and piston regardless of angle or acceleration. By July 1943, they had a working prototype engine that could deliver 450 horsepower continuously without overheating or starving for fuel. Dynamometer tests showed the engine could maintain maximum output for 6 hours straight, longer than any realistic combat engagement. The power-to-weight ratio they achieved was unprecedented for tracked vehicles. The M18 would eventually weigh 17.7 tons fully loaded, giving it a ratio of 25.4 horsepower per ton. Compare that to the Sherman's 12.1 horsepower per ton or even the German Panthers' 15.4, and you start seeing how the Americans were planning to win through mechanical advantage rather than armor thickness. But having 450 horsepower means absolutely nothing if you're trying to push 40 tons of steel. The entire M18 design philosophy hinged on one unforgiving equation. Weight is the enemy of speed. Every single pound added to the vehicle directly reduced its mobility advantage. The engineers at Buick faced a challenge that seemed physically impossible. Create armor that could stop machine gun fire and shell fragments without turning the Hellcat into a sluggish target that defeated its own purpose. Traditional American tank armor was rolled homogeneous steel, typically 50 to 75 millimeters thick on Sherman frontal plates. That kind of protection weighs roughly 40 pounds per square foot. If they'd armoured the M18 to Sherman standards, it would have weighed 35 tons and been lucky to hit 30 miles per hour, completely negating the speed advantage that made the design viable. So the design team made a decision that would be argued about for the next 80 years and beyond. They slashed armour thickness to an average of 12.7 millimeters, with the frontal plate maxing out at just 25 millimeters. To put that in perspective, that's about as thick as 3 stacked quarters. A German 88mm gun could punch through that armour from over 2,000 yards away like it wasn't even there. German 75mm guns from Panthers could penetrate at any combat range. Even heavy machine gun fire could damage the hull at close range. But here's where the engineering brilliance emerged. The team didn't just make thin armour, they made smart armour. Every plate on the M18 was angled at 45 degrees or greater from vertical. When a shell hits angled armour, the effective thickness increases dramatically because the projectile has to travel through more material before penetrating. Basic trigonometry applied to ballistics. A 25mm plate angled at 45 degrees provides roughly the same protection as 35 millimeters of vertical armor. Better yet, many shells simply deflect off angled surfaces rather than penetrating. They studied German shell trajectories obsessively, analyzing combat data from North Africa and Italy to determine the most common angles of attack. Then, they angled every surface to maximize deflection probability. The glacis plate at the front slope was set at 50 degrees. The turret front at 45 degrees. Even the hull sides had a slight outward angle. No surface presented a flat perpendicular target to incoming rounds. The material selection was equally revolutionary for its time. Instead of using steel throughout, engineers incorporated aluminum components wherever structural loads allowed. The transmission housing, engine deck panels, and internal bracing used aluminum alloy 356, which offered 60% of steel's strength at one-third the weight. The road wheels were aluminum. The turret basket, the rotating floor inside the turret where the crew stood, was aluminum mesh instead of solid steel plate. Every component was analyzed for weight savings. Even the ammunition racks used aluminum framing. These decisions saved approximately 2.3 tons compared to an all-steel design of equivalent structural strength. The turret design itself was aerodynamic in a way no previous American armored vehicle had been. Instead of the boxy angular turrets on Shermans, the M18's turret was a smooth, rounded casting that reduced air resistance at high speeds. This might sound trivial, but at 55 miles per hour, aerodynamics matter. Wind tunnel tests at General Motors Proving Grounds showed that the streamlined turret reduced drag by 18% compared to conventional designs. At highway speeds, that translated into less engine strain and better fuel economy. The difference between 150 miles of operational range and 125 miles on the same tank of fuel. In combat operations where supply lines stretched thin, that extra range could mean the difference between reaching an ambush position or running dry before contact. The final weight came in at 17.7 tons, fully loaded with crew, ammunition, and fuel. That's lighter than some World War I tanks and less than half the weight of a Sherman. Critics called it a death trap, with armor so thin that crew survivability would be terrible. Proponents called it a scalpel, precisely designed for a specific tactical niche. Both were right. The M18 was never meant to slug it out with Panthers in frontal engagements. It was designed to avoid those fights entirely by being somewhere else when the shooting started. You can have all the horsepower in the world and featherweight armor, but if your transmission grenades itself the first time you stomp on the accelerator, you've just built an expensive paperweight. This is where most high-speed armored vehicle designs fell apart in the 1940s. The mechanical components couldn't handle the stress of translating raw engine power into actual movement without destroying themselves. The Hellcat needed a transmission that could handle brutal acceleration from standstill, sustained highway speeds for hours, constant gear changes in combat maneuvering, and the occasional emergency reverse at full throttle when ambushes went wrong. General Motors assigned the problem to their Hydromatic division, the same team that had revolutionized automatic transmissions in civilian cars just 5 years earlier. But tank transmissions faced challenges that made passenger car engineering look simple. We're talking about 17 tons of vehicle accelerating from 0 to 30 miles per hour in under 15 seconds, then slamming into reverse to back out of an ambush position while hostile fire impacts the hull. The torque loads were astronomical. Overheating was a constant threat, because tracked vehicles generate far more friction and resistance than wheeled vehicles. Every gear change had to be smooth, or the drivetrain would tear itself apart. The solution they developed was called the torquematic transmission, and it was legitimately decades ahead of its time for armored vehicle applications. Instead of the manual crashbox transmissions that required double clutching and driver finesse, the kind that left Sherman drivers with aching legs after full days of combat driving, the Torquematic was a semi-automatic 3-speed design with a torque converter built in. The driver still shifted gears manually using a floor-mounted lever, but the torque converter acted as a fluid coupling that absorbed shock loads and prevented the drivetrain from tearing itself apart during aggressive driving. Think of it like a hydraulic cushion between the engine's explosive power and the transmission's mechanical gears. Here's the technical magic that made it work. The torque converter used transmission fluid spinning at high velocity to transfer power from the engine to the gearbox. When the driver needed gentle acceleration for precise maneuvering, the fluid coupling allowed slippage, making the vehicle smooth and controllable even at walking pace. When the driver floored the accelerator demanding maximum power, the converter locked up mechanically and transferred nearly 100% of the engine's output directly to the tracks with minimal power loss. This dual-mode operation meant rookie drivers could operate the Hellcat without stalling or jerking during their first combat mission, while experienced crews could extract maximum performance when it mattered most. The margin between life and death often came down to whether you could accelerate smoothly out of an ambush position or stalled the engine trying. The gear ratios were carefully calculated for both speed and tactical flexibility across different terrain. First gear could pull the Hellcat up a 60% grade, a slope steep enough that you're practically climbing a wall. That low-end torque multiplication was essential for combat in hilly terrain like Lorraine, where the fighting would eventually concentrate. Second gear was the sweet spot for cross-country operations, maintaining 25 to 35 miles per hour over rough terrain without beating the crew to death with vibrations or over-revving the engine. Third gear was the highway cruiser, capable of sustained 50-mile-per-hour runs on European roads with engine revolutions per minute, sitting in the efficient range around 2400, where fuel consumption was minimized and mechanical stress remained manageable. Each gear was helical cut instead of straight cut. That technical detail made an enormous difference in operation. Helical gears have teeth that mesh at an angle, distributing load more evenly across the tooth surface and reducing the screaming whine that made older tanks sound, like tortured machinery. The Hellcat's transmission was notably quieter than Sherman gearboxes, giving crews better ability to hear radio communications and detect approaching enemy vehicles. Cooling was solved with a dedicated oil cooler mounted in the airstream behind those massive engine cooling fans. The transmission fluid circulated through aluminum cooling fins that dissipated heat even during prolonged high-speed runs. Field tests in the Mojave Desert during August 1943 proved the system could handle 100-degree temperatures while running flat out for 2 hours straight, longer than the fuel tanks could sustain anyway. The Torquematic's reliability rate in testing exceeded 98%. Failures were almost unheard of, even under abuse that would have destroyed conventional manual transmissions. When M18s eventually reached combat in 1944, transmission failures would be statistically negligible compared to every other. Mechanical breakdown category. The engineering had worked. Now let's talk about what happens when you take a 17-ton vehicle and drive it across bomb-cratered roads, muddy fields, and railroad embankments at 55 miles per hour. Without a suspension system engineered for that kind of punishment, the Hellcat would have shaken itself to pieces. Broken axles, thrown tracks, turned its crew's internal organs into scrambled eggs from the violent impacts. The faster you go, the more violently every bump, dip, and obstacle translates into vertical force, trying to tear your vehicle apart. At low speeds, suspension is about comfort. At highway speeds in a combat zone, it's about survival and maintaining the ability to fire accurately. The engineering team chose torsion bar suspension, and this decision was absolutely critical to everything the Hellcat could do tactically. Here's how torsion bars work. Instead of coil springs or leaf springs like you'd find in trucks, torsion bars are long steel rods anchored to the chassis at one end with the other end connected to the swing arm that holds the road wheel. When the wheel hits a bump, the swing arm rotates, twisting the torsion bar along its length. Steel's natural resistance to twisting provides the spring force that pushes the wheel back down. The system is elegant in its simplicity. The genius of torsion bar suspension is that these bars are incredibly compact, freeing up precious internal space for ammunition, storage, and crew positions, and they're progressive in response. The more you twist them, the stiffer they become, which prevents bottoming out on hard impacts while still providing soft initial compliance over small bumps. The M18 used 6 dual-wheel bogies per side, each with its own independent torsion bar. The bars themselves were manufactured from chrome silicon alloy steel, heat-treated to a specific hardness that gave them a service life exceeding 5,000 miles, even under combat conditions. Each bar was 1.5 inches in diameter and roughly 4 feet long, carefully calibrated to handle the Hellcat's weight distribution. The front bars were slightly softer to absorb initial impacts as the vehicle charged over obstacles. The rear bars were stiffer to handle weight transfer during acceleration and the massive recoil force from firing the main gun, which tried to lift the front of the vehicle off the ground with every shot. But torsion bars alone weren't enough for highway speed operations. At 55 miles per hour, hitting even a small pothole generates enormous oscillation. The vehicle wants to bounce repeatedly, and each bounce throws off the gunner's aim and fatigues the crew. Combat effectiveness degrades rapidly when your crew is being beaten unconscious by their own vehicle. So engineers added hydraulic shock absorbers to the first and last road wheel stations on each side. These shocks worked exactly like high-performance car shocks, using oil forced through calibrated valves to dampen oscillations. The result was a suspension system that could absorb a 2-foot vertical drop at full speed without the crew experiencing whiplash or the gun barrel slamming into its elevation limits. Testing proved the system could handle jumps that would have destroyed Sherman's suspensions. The track system deserves recognition here too. The Hellcat used 16-inch wide center guide tracks with rubber chevron pads. That rubber contact patch was essential for multiple reasons. It reduced ground pressure to just 10.7 pounds per square inch, meaning the Hellcat could cross soft ground that would bog down heavier tanks. The rubber also absorbed high-frequency vibrations that steel tracks transmitted directly into the hull, vibrations that would fatigue crews and damage delicate equipment like radio sets and gun sights. Each track assembly had 86 links per side, and the guide horns kept the track centered on the road wheels, even during violent maneuvers at speed. Track throwing, when a track comes off the drive sprocket during hard turns, was a constant problem with fast-moving armoured vehicles. The M18's track design minimised this risk through careful engineering of the guide horn placement and tension adjustment systems. During testing at Aberdeen Proving Ground in October 1943, engineers drove an M18 prototype through an obstacle course at maximum speed. The course included 18-inch deep trenches, 30-degree side slopes that would roll most vehicles, and vertical walls that tested approach and departure angles. The suspension performed flawlessly. Measured vertical acceleration inside the crew compartment stayed below 2 gs, even on the hardest hits. For comparison, Sherman crews regularly experienced 3 to 4 G impacts on rough terrain, enough to cause concussions if heads struck the turret interior. Crew testimonials from training exercises consistently praised the Hellcat's ride quality. Drivers reported they could maintain 40 miles per hour over terrain that forced Shermans to slow to 15. Gunners could keep targets in sight through rough ground because the suspension isolated the turret from hull motion sufficiently that the gun sight picture remained relatively stable. That stability translated directly into first shot hit probability, the single most important factor in armoured combat. The ability to engage targets accurately while moving fast was exactly what General Bruce had envisioned. You arrive at the ambush position before the enemy knows you're there. You fire from an unexpected angle while they're still trying to identify the threat. You hit on the first shot because your suspension keeps the gun stable. Then you vanish before return fire arrives. Speed, accuracy, survival. The engineering made it possible. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen. Now, and don't forget to subscribe.